Okay, stats, we're going to do example 13, which of course is another box plot because can't get enough of those babies. All right, so we're looking at example 13 and 14 together here because they kind of have to do with each other. So what I'm going to do, I'm going to go over to our survey data and I'm just going to grab some pulse rates here. All right, so I'm just going to grab these. Just going to copy that. And then I'm going to go into Staplet. And I'm going to go into one quantitative variable single group. I'm just going to paste those babies right in there. All right, begin analysis. Okay, so look at the dot plot. Does it look like 120 is far away from the data? Yes, Ms. Griggs, it does. Okay, is it an outlier? Gee, I don't know. Okay. Histogram. Is the 120, is there space between it and the rest of the data? Yes, Ms. Griggs, there is. Is it an outlier? I can't be sure. Look, Ms. Griggs, it looks like that 120 is far away from the data in the stem plot. It may be an outlier, but do I know? No, I don't. Look, Ms. Griggs, look how pretty that box plot is. See that 120 right there? It's an outlier. How can you say that, my children? How do you know it's an outlier? Because it's outside the scope or the design of the box plot. You see that? Okay, it's out there all alone. The box plot's the only graph that the graph itself can tell you there's an outlier. Okay, so going back to our example, I have saved this picture already. I'm going to insert it right here. All right, so how am I going to talk about this? Well, there's clearly an outlier. That means that the general shape of my graph is approximately skewed to the right. An outlier by nature is going to automatically change the shape of that graph. So I am going to write the pulse rates are somewhat. Oh, Miss Griggs, your handwriting is out of control. You don't have to say somewhat. You can just say it's right skewed. The pulse rates are somewhat right skewed. Due to the presence of an outlier at 120. The median pulse rate. Yes, context is important. You have to use it at least once in every single description. The median pulse rate, it's called good communication. The median pulse rate is 75 with an IQR of, we got to find that. So the IQR, remember, is Q3 minus Q1, which is 84 minus 69.5. So that'd be 14.5. Awesome. So that is the answer to 13. Okay, we indicate that we know there's an outlier because it's a box plot. Now, I want to caution you here. If this had been a histogram, you cannot say it is an outlier. If you just had the graph, like just the histogram, you could say you believe there may be an outlier. And even then, you can only say it's between two values. You're not sure what's in that bin. If you had had the summary statistics, see, we have the summary statistics. So if you were to have created a histogram, you could use the summary statistics to run the outlier test, and therefore you could say for sure if there's an outlier. Okay, so here's what I want to do next. I want to continue with example 14 because it's about running an outlier test. So your data from example 13 had an outlier. We've already talked about that. If you are asked to do an outlier test, you must confirm the outlier mathematically. Show the outlier test using the data from, this should be example 13. Typos, grr. Anyway, So I explained the outlier test in one of our other videos, but now we're going to apply it to this problem. So here's the deal, and I emphasized this in the video, hopefully you were listening. The outlier test just gives us boundary values, all right? We want a boundary below Q1, that's why it's Q1 minus 1.5 times IQR, and we want an upper boundary, which means we're going to have Q3 plus 1.5 times IQR. This formula is not on the formula chart. You do have to know this. All right, so the Q1 I know already is 69.5 minus 1.5 times the IQR, which I just found to be 14.5. So that's going to be 69.5 minus 1.5 times 14.5. Don't forget to follow PEMDAS. You don't do the subtraction first, you do the multiplication first. So this number is 21.75, and when I subtract that, I get 47.75. Okay, so that's my lower boundary. Q3 now is 84. Why did I do that? I tell you what, for crying out loud. Sorry, kids. Okay. So now 84 plus 21.75 gives me 105.75. And don't be too impressed. I didn't do all that in my head. I used a calculator. So, all right. So these are boundaries. And to illustrate this, I want you to notice something, because a lot of students struggle with this. They look at these values and they think that these boundary values are pieces of data that are present in our list. But let's go back to our data survey. Do you see 47.75 anywhere in that blue area? No, you don't. What about 105.75? No, you don't. That's because the outlier test just gives you boundaries within your data. So let me illustrate to you what I am talking about right here. All right, 47.75 would be somewhere over here, okay? Clearly, within our data that we have, nobody had a pulse rate lower than that. So that lower boundary indicates that we do not have a lower outlier. The 105.75, on the other hand, is about right here, okay? Those are boundaries. So anything on the outside of the boundaries from your data, anything outside those is an outlier. So clearly we have mathematical evidence that 120 is an outlier. So how would I write that? I would say 120 is an outlier because it is greater than 105.75. Or you could say it falls above the boundaries for my outlier test, or anything like that. But you have to show this mathematically. If you are asked to run an outlier test, or you're trying to say there's an outlier in a stem plot, a histogram, or a dot plot, you have to run the outlier test. Notice the pieces you need for the outlier test. You must know the Q1 and you must know the Q3, because the difference of those produces your IQR. All right? If you don't have those pieces of data, those values in the data, you can't run the outlier test. Awesome.